Hello, Physics Nation. My name is Nate Larmond, and this is video 4 in the truss analysis series. Let's see, where are we? We are beyond pin joint C. So we found the reaction force. That is the upwards force right here. I think that was 775 pounds. We found the compression force. I think that was 1,096 pounds. Then we found the tension force. That was 775 pounds again, because this angle is 45 degrees. And now we are moving on to joint E. We have a load of 500 pounds. This is a compression force, like I said. So if it's pushing on joint C, it's also pushing on joint E. That's sort of important. We have some kind of force in this guy, DE, and we have some other kind of force in this guy, BE. So I think we're going to focus on this force right here. In class, we assumed this guy to be tension, that is pulling away from joint E, because I think somebody said, well, this is pushing in the positive Y direction, so maybe this is pulling in the negative Y direction. I think somebody else also said if this guy is, well, I don't know. Somebody said at the top it was probably under compression, and at the bottom it was probably under tension. So I think we assumed this guy to be pushing to the right, but we did not find this compression force. We found this tension force. So how did we do that? Well, looks crazy complicated, but again, it's just F equals ma. These are statics problems. The sum of the forces are 0. If the system isn't accelerating, it's in a state of balance, except the system this time is joint E at the top of this truss, the top right-hand side. So we got the negative 500 pounds. We've got 1,096 coming in at 45 degrees above the horizontal, and we have this force. This is what we're going to focus on, the tension in member EB. We define this geometry to be 56 degrees below the horizontal, but there's nothing wrong with finding, opposite and adjacent using 56.3 degrees, but then you need to know, oh, this is negative X, this is negative Y, I'm in the third quadrant. A better way to describe this angle is to rotate counterclockwise from 0 degrees, that is the positive X axis. So half a rotation is 180 degrees, and then we just went 56.3 degrees beyond 180. So you just take 180 plus 56.3, and that is 236.3. So if you do counterclockwise from 0, the signs of the X and Y components will turn out automatically correct, and you don't need to think, is this left, is this right, is this up, is this down? Anyway, that's my suggestion. You can use 56.3. Just remember to double check your signs. So, like I said, it's all about Newton's second law. F equals ma. The sum of the forces are 0, and we are in the vertical direction. So we've got negative 500. We want the Y component of EC. Well, we just found that. EC is 1,096, and sine of 135 degrees is 0.707. So the 775 pounds of force just turns up over and over and over again. We're going to combine that with the negative 500. The math teachers say combine like terms to be positive 275 pounds. And what is the vertical portion of EB? Well, it's just hypotenuse sine of theta. And here we go. It doesn't look like hypotenuse sine of theta, but 100% of the force is the hypotenuse. So here we go. Hypotenuse sine of 236.3 plus the other two vertical forces is 0. We have 3 vertical forces acting on this guy. The vertical portion of EC, the vertical portion of EB, and 100% of this negative 500 pounds. What is the sine of 236.3? Well, that is negative 0.832. That is, what percentage of this force is down. Well, 83% of it is down because it's not 45 degrees, it's beyond 45 degrees. So that sort of makes sense that it's, greater than 0.707. And what are we doing here? We're going to add negative 275 to both sides. This negative on the right cancels with the negative 0.832 on the left. That means our assumption of tension was correct. If your sign doesn't flip at the end, that means you guessed the correct direction. So 275 divided by 0.832 is 330 pounds. It's kind of interesting that the outside member is almost triple the force of this inside member. And the outside member is under compression, but the inside member is under tension. And so, like I said, in maybe part 5, we're going to find the force in the top member, DE. Somebody in class suggested it's a compression force, and we're going to test that hypothesis in the next episode. Thanks for watching.